Hello everyone, and welcome to OneClass. My name is Jeff Krause. I have a PhD in physical chemistry, and today I'm going to run through a few undergraduate high school level chemistry questions. So here's our first one. So it reads, the 4 bonds of carbon tetrachloride are polar, but the molecule is nonpolar because the bond polarity is cancelled by the symmetric tetrahedral shape. So just to draw this out, right, so we've got where I'm using this wedge to show that it's coming out of the page, and this dashed bond to show that it's going into the page. And so the idea here is we've got each of these dipoles set up, but because the molecule is completely symmetric, each dipole cancels, and so it differs a bit the way it's drawn between physics and chemistry, and I don't actually remember which way I default to, but I put the positive end at the plus and the negative end at the arrow, so my dipoles are pointing, I think it must be the chemistry way because it's pointing from positive to negative, which is the opposite to the definition of dipole, but that's fine as long as it's consistent. So as you can see, all the dipoles point out, but then they would all cancel. Okay. Okay, so now when symmetry is broken, we're going to get a dipole, and it wants us to rank several molecules. So I'm just going to draw them out as I come to them. So I've got C, H, bromine, and bromine. And I'm just going to draw a bunch of them. And of course there's other stuff down here. Okay. Okay, so CF2, CL2, C, it's supposed to be a wedge shape, F, Cl, and I'm not putting any atoms in any particular position for any reason. I'm just doing it based on wherever I decide to add it. And it shouldn't matter. For the answer, it won't matter where they go, as it shouldn't, because the molecule is symmetric, so if you rotate it, well, these ones won't be symmetric, but if you rotate it, you should be able to get to any orientation. Okay, where am I here? There we go. I'm just going to keep adding and erasing this stuff. Okay, that was that. So C, H, Cl2. And now CBr4. And CF2Br2. Okay. CF2. Oops. Should be Br2. carried away. All right, there you go. Now, okay, so now it wants us to rank these molecules from least polar to most polar. So to do that, we need to consider what each bond's polarity is and how it's going to add up in the molecule. So if we're looking for polarity, we're really looking for either electronegativity or electron withdrawing strength. So if you look at a periodic table, it basically increases from bottom left to top right. So that means that fluorine is going to be greater than chlorine, which is going to be greater than bromine, which is going to be greater than carbon, which is going to be greater than hydrogen. Okay, so then our dipoles are going to, at least in this, in my definition of drawing it from positive to negative, we're going to get dipoles set up in this molecule like this, as it's going to point towards if I'm pointing towards the more negative end, it's going to be towards carbon and CH bonds, towards bromine in the carbon-bromine bonds. This guy is going to point towards each of the halogens. So here we've got this pointing towards each of these. This is going to point now towards the carbons and towards the halogens. This one's going to point towards each of these bromines. And then this one is again going to point towards each of the halogens. Okay, so now we've drawn on some dipoles. If we look at this ordering here, so a CF bond is going to be more polar than a CCl bond, which is going to be more polar than a C bromine bond. And the carbon-hydrogen bonds, if we look at, say, this molecule here, it's actually going to add up the dipole. So it's our carbon bromines are trying to draw the electron density towards the bromines, and the hydrogens are just going to help that. So this is going to actually just increase our dipole. So all the hydrogen ones, so this one, and this one are obviously going to be our highest ones. And looking at this ordering, it's going to go fluorine higher than chlorine, higher than bromine. So we can start to rank here. So C2F2 is going to be greater than C2Cl2, which is going to be greater than C2Br. I missed some hydrogens in there. I'm just gonna erase it and start over again. So I started off badly. So CH2 F2 is going to be greater than CH2Cl2 is going to be greater than CH2 Br2. So our dipole is going to kind of run in that order, at least for the hydrogen containing ones. Okay, so now we're left with three molecules, these three here. Now they both contain fluorine and another halogen. If we look at the directions, these are canceling, right? So we've got some cancellation, right? So the carbon-chlorine dipole is higher than the carbon-bromine. So in this case, we've actually got more cancellation due to the chlorines as compared with the bromines, right? Because the bromine dipole is less. And so that means that this guy should be higher because the bromine's dipole is smaller. So then that's greater than CF2Br2, which is greater than CF2Cl2, right? And so the fluorine-containing species with the bromine is going to be higher than the chlorine just because of smaller cancellations. And then if we look at this guy, we've got complete cancellation because it's symmetric again. So this dipole is 0, right? So then that's going to be our smallest, CBr4. And so then that's going to be our ordering. And now if we check through here, so for all carbon hydrogen bonds, so for all carbon halogen bonds, it's going to go in the order of electronegativity, so fluorine, chlorine, bromine. And then hydrogen is just going to build it up. So, and CBr4 is non-polar because it's symmetric. So the ordering is just from smaller to higher here, whereas I did it from highest to lowest. So CBr4 is less than CF2Cl2, is less than CF2Br2, is less than CH2Br2, is less than CH2Cl2, is less than CH2F2. Okay, so that's our highest, and so the ordering looks the same to me. And so I would say the solution is correct. Okay. All right, so what is the mass percent of hexane in a mixture with heptane if the mole fraction is 0.2? And we actually don't need the figure in this case. It's relevant, but it's related, but not really relevant to the question. Okay, so we've got a hexane, and just as a reminder, this is C6H14. So we've got a hexane-heptane mixture, which is C7H16. And we've got a mole percentage, which is N of hexane over N total, which is 0.2. And it wants to know what MC6H16 over M total, what that is. Okay, so our N total is just the sum of our moles. And I'm getting carried away. Plus that for heptane. Our mass total is then the sum of our masses, which we can write as our moles times our molar mass for each of these species. Okay. Now, if we write our MC6, oh, okay. And we can use the fact that we also know our moles of our mole fraction for C7H16, because if our moles for hexane, our mole percentage for hexane is 0.2, then while our mole percentage for heptane must be 0.8, because it needs to add up to 1. So our mass total over our N total is then NC6H14 times over N total times MC6H14 plus N of heptane over N total times our molar mass for heptane. So just using the factors we have, this is then 0.2 plus 0.8, or our mass total is then just 0.2 C6H14 plus 0.8 our heptane mass times our N total. Okay, so now our mass for hexane, I want to get these mixed up, C6H14 over our mass total is then equal to, so our mass for hexane is just our molar mass for hexane, our moles for hexane times our molar mass for hexane over our total mass, which we've just written in this way. So I'm actually going to bring the N total out front just to make it obvious. Okay. And now out front here we again have our mole fraction of hexane, and so then that's just 0.2 times our molar mass of hexane over, and so now we have it completely in terms of our molar masses. And so we can now readily figure out what our mass percentage would be. So our molar mass for hexane, or first actually our molar mass for carbon is 12.01 grams per mole, and our molar mass for hydrogen is 1.008 grams per mole is what I'm going to use. So our molar mass for hexane is 6 times 12.01 plus 14 times 1.008, which is then 86.172 grams per mole. And our molar mass for heptane is going to be 7 times 12.01 plus 16 times 1.008, which is then 100.198 grams per mole. All right, so there's our molar masses. We have our equation for our mass percentage. So then mass percentage of hexane is going to be then 0.2 times our molar mass for hexane, which is 86.172 grams per mole, all over 0.2 times 86.172 grams per mole plus 0.8 times our molar mass for heptane. Okay, and then working through this on our calculator, we get 17.2344 on top, and oh, I guess I wrote it right out, so 80.1584, and then working through this on our calculator, we get 0.1770, or in percentages, so multiply by 100%, and it's 17.70%. So our mass percentage is 17.70%. So now going through the solution here, assume a mole of mixture, so that's fine. If it helps to do it that way, that might be easier. So we just solve for a mole of mixture, and because it's going to be a percentage, then it should be unitless anyway, so it doesn't matter what volume or what moles you choose to work with. So if you work with a mole, well, your mole fractions are still going to be the same. You'll get an amount of grams, which is fine, and so you'll get a gram, a mass amount for this fictional number of moles, but then the mass percentage will always carry over, and it comes out to be 17.71%, but that's likely just either rounding errors or differences in choice of our just number of decimal places. So, and also likely choices, it looks to be difference in molar masses used for carbon and hydrogen, just because hexane comes out to be 86.18, whereas I've got 0.172, and yeah, so it's likely just differences in molar masses, but the solution, I would say, is correct. Okay. Which has the larger second ionization energy, lithium or beryllium? Okay, so this is my third. I didn't really number the last one, but it's okay. All right, so lithium is, if we look at our electron configuration, 1s2, 2s1, and beryllium is 1s2, 2s2. So to look at ionization energy, either first or second, general rule of thumb is going to be that it's easier to remove a valence electron as opposed to one of the inner shell electrons. So right away we can kind of see which one's going to have the higher second ionization energy. So our lithium is going to go to lithium plus, whose electron configuration is 1s2, and then for the second ionization energy, it's going to go to lithium 2 plus, which has a 1s1 electron configuration. So here we're removing a 1s electron. Well, I guess it'd be more like that. So for beryllium, we're going to go to beryllium plus, which is 1s2, 2s1, and then we're going to go to beryllium 2 plus, which is just 1s2. So in this case, we're removing a 2s electron. So in any case, a 2s electron is going to be further from the nucleus. So if we look at our energies, which ionization energy, remember, is the difference in energy between completely removing it and where it lies in the shell. And although this is only true in hydrogen, we can say that it's approximately proportional to 1 over n squared, which is in a hand-waving way true, although it's not true unless it's hydrogen. But it's going to be approximately proportional to 1 over n squared, minus 1 over n squared, I should say. That means that an n equals 2 electron, which is this, is going to be a lower energy to remove than a 1s electron. And so our beryllium plus is going to have a lower second ionization energy, which means that lithium should have the higher second ionization energy. Okay, the ionization energy of an atom or ion is the minimum energy required to remove an electron. Remove the second, the energy needed to is on the side for this. Okay, first energy level is close, thus lithium would have a larger. Yeah, okay, so lithium's higher, so that's good. So that looks correct. Although there's a bit of extra text in there. Okay. Okay, so now this one is to rank these acids from weakest to strongest. They're all carboxylic acids. So I'm just going to go through the 4 acids that are shown here. It's a little cut off at the bottom, but it's not too big a deal. So first of all, we've got carbon, carbon. Oops. All right. OH. And so the acidity is going to depend on how readily, the acidity in all cases is going to be how readily we can break this bond and yield this H+. So how readily that can be done is always going to be determined by how weak the bond is. So we want this bond to be weak, and that will make it a strong acid. And the weaker the bond, the stronger the acid. Okay. So in this case, these CH3s on the end are actually with electron donating groups, meaning they're going to donate electron density this way or along the molecule, meaning we're actually going to strengthen the bond. So this is likely our weakest acid unless there's something with more electron donating groups. So now we've got CH3, C, OOH. This is kind of our neutral carboxylic acid, or not our neutral, I shouldn't say that. This is our basic, I guess I shouldn't use basic either, our standard carboxylic acid. So this is kind of our comparison ground. So that one, I'm not going to make any comments necessarily. So this is kind of what we're going to compare everything to. So we've got bromine 3C, COOH. Now the bromines are electron withdrawing groups. So now these are going to pull electron density away. And these are actually now going to start weakening. And their electron withdrawing ability is directly correlated with their electron affinity. So if we compare this now to our last molecule, which is CF3, then this is now the same. It's also going to draw electron density away and weaken that bond, but fluorine is greater than bromine, and so this one is going to be the stronger acid. This one here is going to be the weaker acid, as we said. And bromine is going to be stronger than our standard acid, our standard carboxylic acid. And so now we have our ranking here. So it's going to be CH3CCOOH is less than our CH3COOH, which is going to be less than B. I don't know, just try to emulate now one of the answers so we can compare it. CBr3COOH, which is going to be less than our CF3COOH. And if we look, that's just answer A. So it's the top answer. So that looks good. Okay, so there's our general form for our carboxylic acids. And the increase in acid strength is going to be whether we can... so another way of phrasing what I said is whether or not the conjugate base is stabilized, or how well it can take the negative charge. So essentially the same thing. So either how weak the bond is to the hydrogen, or but the weakness of the hydrogen bond is directly proportional to how well the conjugate base can stabilize the negative charge. So in the end, it comes across the same. So this is whether it stabilizes the negative charge, or whether you have, or the strength of your electron withdrawing groups. The methyl group, the acid strength will be lower because they're electron donating groups. And with halogens, you're going to get a stronger acid strength. So with those in mind, we can say the correct answer is A. So that looks good. All right. Okay, so what is the correct order of increasing first ionization energy for the following elements? So if we look at a periodic table, we'll notice that these go right across our second row. So our beryllium is 1s2, 2s2. Our boron is 1s2, 2s3. Carbon is 1s2. Oops, it's not 2s3. It's 2s2, 2p1. 2s2, 2p2. Nitrogen is 1s2, 2s2, 2p3. And oxygen is 1s2, 2s2, 2p4. Okay. So our first ionization energy is going to be kind of a mix of things here. So in all cases, our valence electrons, which will be the ones that are removed, are in n equals 2 states. So our energy is going to be approximately proportional to minus 1 over n squared. So in each case, we've got an n equals 2 states, so that it appears to be the same. So we need now to know what this proportionality is. Actually, I guess it'd be better for me to put in the z. So it's going to be approximately proportional to minus z over n squared, where z is our nuclear charge. Okay. So across this, our nuclear charge is increasing, right? So our beryllium here is 3 plus, as far as in the nucleus. Our boron nucleus is 4 plus. Our carbon, no, I messed something up here. No, 5 plus. Oh, 4 plus, sorry. So beryllium's 4 plus, boron is 5, carbon is 6, nitrogen 7, and oxygen is 8. Okay. And remember that this is negatively charged, or not negatively charged. Remember that the energy is negative, meaning you've got a larger ionization energy, which is going to be defined as our energy of infinity minus our energy for our valence. Okay, so then our ionization energy is approximately proportional to z over n squared. Right. So that means that as oxygen has our highest nuclear charge, and they all are in an n equals 2 state, we would expect oxygen to have our highest ionization energy, and then we'll go down with nuclear charge, basically. So our oxygen should be greater than our nitrogen, should be greater than our carbon, it should be greater than our boron, and should be greater than our beryllium. And I will point out here that I am saying that this is approximately proportional because there are other factors that are going to come in. And as we move down the periodic table especially, we're going to need to worry about shielding, especially as we determine that an approximate nuclear charge. But going across from left to right across the table, this works pretty well. So now if we check the solution here, so it increases from left to right across a table and decreases down a group. If we look at the ordering of our ionization energies, it's oxygen greater than nitrogen, greater than carbon, greater than boron, greater than beryllium. So that looks good. I apparently like to do things from highest to lowest. I guess it is order of increasing, so I'll just swap that around so that I'm at least consistent with the answer they expect. So that's good. Okay, so this one is just an acid-base question. So what is the pH of 0.390 molar ammonia? So first off, we need the Kb for ammonia, which comes out to be, I should at least write it out. So Kb ammonia is 1.8 times 10 to the minus 5. Okay, so our ammonia is going to combine with water to give us, so our H plus is going to transfer this way to give us NH4 plus OH minus. Now we can make our ice table. So we have 0.390 and nothing of these initially. Our change is going to be minus X plus X plus X. And that's just because we're in a 1:1:1 mole ratio. And so at equilibrium, we're going to have 0.390 minus X, X, and X. So we can write our equilibrium expression as our products over our reactant, remembering that pure substances like water are not included. And so this is just X, X, and 0.390 minus X. And now I'm going to make a simplifying assumption that because Kb is 1.8 times 10 to the minus 5, that our X is probably very small, and so this is approximately 0.390. And so this will just save us from having to use quadratic equation. And so our X squared is 1.8 times 10 to the minus 5 times 0.390, which is 7.02 times 10 to the minus 6. So X is 2.65 times 10 to the minus 3. And we can see the validity of this assumption, because 0.39 minus this is approximately 0.39, I would say. Okay, so now this is our OH minus concentration, but we're asked for pH, which is the negative logarithm of the H plus or H3O plus concentration. So to move this to H3O plus, we can use a few means. The one I'm going to use here is just that our water ionization scheme looks like this, right? And so Kw is a constant, 1 times 10 to the minus 14. And if we look at what we have here, and I shouldn't have put these square brackets in, I carried away. If we look at this expression, products, so it's just going to be the product of our H3O plus and our OH minus concentration. And we know our OH minus concentration, so we can solve for our H3O plus concentration. And so our H3O plus is just 1 times 10 to the minus 14 over our OH minus, which comes out to be 3.77 times 10 to the minus 12. Units with equilibrium stuff is wonky, so I'm just going to add it in whenever we know it, which would be there. And so then pH is the negative logarithm of our H3O plus concentration, which is the negative logarithm of 3.77 times 10 to the minus 12, which is 11.42. Okay, so there's our pH. All right, so we need our Kb for ammonia. We use our ice table, solve for, so they did use the quadratic equation. So it comes out to be 2.65 4 times 10 to the minus 3. I got 2.65, so that's possibly just, that's possibly rounding errors, but it's also possibly due to that assumption I made. And now, so now we can either use the method I use to swap to the H3O plus concentration, or you can go directly to pH by first finding your pOH, and then using that the sum of the two must be 14, which is what they've used here in step 5, and then you get that your pH is 11.42, which is exactly what we found here. So this looks good and shows kind of a different method. Okay. So here the question's a bit cut off, but I'll add to it. So here's our equation for conversion of carbon dioxide with potassium peroxide. Which we will need at some point. So this takes in carbon dioxide and gives oxygen. I'm just going to scroll this down a bit. Okay, so now the question is if we are creating air at a rate of 3 liters per minute, and our CO2 is 0.034 of air. So that means that for our CO2, we are creating 0.034 times 3.0 liters per minute. Okay. And then the question asks, how much potassium peroxide in grams do we need for a 5-day trip? And so, yeah, I think that's enough to solve the question. So in a 5-day trip, we need to know our volume of CO2. And so that's going to be our rate of CO2 production. I'm going to just solve this through. So if we put this through our calculator, then we're producing 0.102 liters per minute. And so our total volume in 5 days is going to be 0.102 liters per minute times 60 minutes per hour times 24 hours per day times 5 days. So our days will cancel, our hours will cancel, and the minutes will cancel, leaving us with an answer in liters. And so this gives us 734.4 liters. And now, given a volume of CO2, all right, now I remember what else is in the question. So the other stuff given in the question is that our ideal gas constant is 62.363 millimeters of mercury, liters per mole Kelvin. Our temperature is 250 Kelvin, which is extremely cold. It's like negative 20-some degrees, but okay. And our pressure is 728 millimeters of mercury. So now with the ideal gas law, we can solve for the number of moles of CO2 that this involves. So we can rearrange and say that our number of moles is PV over RT. which is 728 millimeters mercury. Our volume that we computed above, which is 734.4 liters, over our gas constant, which is 62.363 in our appropriate units, and our temperature, which is 250 Kelvin. All right, so then that cancels, and that cancels, and that will flip up to the top to give us an answer in moles, so that looks good. If we run this through our calculator, we get 34.292 moles. And now, if we look at our balanced chemical equation above, we can see that our potassium peroxide and our carbon dioxide are in a 2-to-2 ratio, which is another way of saying a 1-to-1 ratio. So we have a K2O2 to CO2 ratio of 1-to-1. So that means our number of moles of K2O2 is just equal to 34.292. So if we have this many moles of carbon dioxide, we need an identical amount of moles of potassium peroxide. So to get mass in grams, we need our molar mass. So mass of potassium is 39.0983. Mass of oxygen, or molar mass of oxygen, is 15.9994. And so our molar mass for potassium peroxide is 2 times 39.0983 plus 2 times 15.9994, which comes out to be 110.1954. Okay, and so we have our moles, we have our molar mass, so that means our mass of K2O2 is just our moles times our molar mass, which comes out to be 34.292 moles times 110.1954, which when we run this through our calculator is 3778.82 grams, or we're given 2 significant figures on our production of air, and so that would just be 3.8 times 10 to the 3 grams. And so that would be our mass of potassium peroxide in grams. So we need PV equals nRT to get the volume. Solving this through. So our gas constant wasn't given in any particular units, so you can use whichever units you want. They converted to atmospheres, which is fine. 34.30 is what they got for their moles, which could be the case for rounding. And depending on rounding errors and how you define your molar mass, the mass in grams comes out to be 377986 for them. A little different, probably due to just definitions of molar mass, but if we round it to 2 significant figures, the 2 answers will be the same. So I'd say the solution is correct. It would only differ in some rounding places. Okay. Now consider the following 4 molecules. Which of these satisfy the octet rule and which do not? Okay, so CO3 2 minus. So here we have just running through some Lewis structure stuff. So here we have 4 valence, here we have 6 valence, And so our total number of valence electrons is going to be 4 plus 3 times 6 plus 2 for the 2 negative charge. And so that's 24. And so if we try to draw this, so we normally have something like this. Or now we'd have an extra electron sitting on carbon because there's only 3. So obviously, to get our full octet, we're going to need to join those two into a double bond. And then we've got 2 extra electrons, so we might as well plunk them around our oxygens. So as we can see, those 2 are going to be negatively charged because they have an extra electron. So that's where our 2 minus comes from. And it looks like everyone has their octet satisfied. So that looks good. PF5. So I'd say this already looks kind of suspicious. Again, we have 5 valence there, and each of these are 7. So the total number of electrons is 5 plus 5 times 7, which is 40. So now to get all of these arranged, we're obviously going to have to expand our octet around phosphorus, which is doable. So this guy is going to have to be able to accept 5 bonds. And now each of the fluorines have full octet, but obviously this guy has an expanded octet. And so does not satisfy the octet rule. Okay, so for CS2, so we've got 4 there and 6 there, so the total is 4 plus 2 times 6, which is 16. So here's our carbon and our sulfurs. So we've only got 2 there, and we've got 4 valence around carbon, so we can be pretty sure we're going to double bond. And then these guys are going to keep their lone pairs, and now this looks like everyone has a nice full octet, so that looks good. And then boron BBr3. So here we've got 3, 7 each, so 3 plus 7 times 3 is 24. So we've got boron, which only has 3 electrons. And then each of these bromines can readily bond in, satisfying their octet. But bromine has only 6 electrons around it, so it does not the octet there. And so boron is also one of the ones where the octet isn't satisfied. And so here our PF5 has an expanded octet, whereas CO3 2 minus and CS2 have their octet, and then the boron bromine compound does not have a full octet. Okay, so digging through the solution here, we need to define what a molecule is. So this is technically true, so CO3 2 minus is an ion. And the definition of a molecule does state that there's no charge. I think that's probably not what is meant by the question, but perhaps it is. So CO3 2 minus is just not a molecule. So I guess because it says consider the following 4 molecules, it might mean not to consider CO3 2 minus, but just in case, I'm going to say it does have a full octet. So for PF5, we have an expanded octet. For CS2, we have our full octet. And then for boron tribromide, we have an incomplete octet. So it's just CS2. I'm going to say this is correct. I'm not sure if they meant for you to just not do the first one, but maybe. So I'm just going to say it's correct, because that looks good to me. And actually, this one's a pretty quick one. So I'm just going to do it up quickly. So when we're looking for a conjugate base, in this case for HSO3, then we're treating this as an acid. And so we're going to transfer H plus to get no H's because we've transferred it, to get SO3 2 minus plus H3O plus, and then HSO3 minus and SO3 2 minus are conjugate pairs. And H3O plus and H2O are also conjugate pairs. So this is acid and base. And so we can identify that our conjugate base is SO3 2 minus. Okay. Bronsted acids are proton donors and bases are proton acceptors. Thus, the conjugate base is what's left after you donate a proton. So in this case, it would be SO3 2 minus. Yeah, so that looks good. And I'm actually going to stop that there and say that's it for today. I hope you've enjoyed this. If you have, please subscribe to the OneClass channel. If you want to leave questions, please follow the links below the video. This has been Jeff Krause for OneClass.